Welcome everyone to PHY 255 Vibrations and Waves. Our study of vibrations and waves will be in the context of differential equations, the necessary background of which we will cover in this first lecture. Let's start with some basic notations and terminology. A differential equation, or just a DE as we will often abbreviate it, is simply an equation that involves an unknown function and one or more of its derivatives, or unknown functions and their derivatives. So for example, something like dy dx equal to cosine of x. This equation is stating that there is some unknown function y in terms of x, and though we don't know what it is, we do know the rate at which it is changing at any x value, or its derivative at any x value is given by cosine of x. Or there's some unknown function v in terms of t and its derivative is given by 9.8. Or there's some unknown function x in terms of t and the rate of change of its rate of change, or its second derivative, is given by 9.8. Now, these are all very basic examples of differential equations, in each case involving some unknown function and one or more of its derivatives. And based on your experience in calculus, specifically differentiation, you should be able to guess what each of the unknown functions in these three equations might be. And based on your background in physics, you should be able to recognize these two. Now, moreover, these are examples of ordinary differential equations, because in each case, the unknown functions involved have only one independent variable. Like here, y is the unknown function, and it has only one independent variable, x. Similarly here, t is the only independent variable, and here, t again is the only independent variable. Whenever there's only one independent variable involved, it is called an ordinary differential equation. And it's the kind of differential equation that we will be concerned with for the majority, though not all of the course. So ordinary differential equations therefore concern functions of this sort. Something, for example, of the form y equal to f of t, where in principle it's easy to differentiate and to interpret a derivative. For example, the derivative at 3, so f prime of 3, or dy dt at t equal to 3, would simply be the slope of the graph at this point, or in other words, the slope of the line tangent to the graph at that point. Now, these aren't the only kind of functions that are of interest in mathematics, or let alone physics. I mean, you could also have more than one independent variable. For example, you could have 2, where here x and y are two independent variables, and for every x and y there is some associated z value through a function that I called psi. Now, differentiation here would necessarily have to work a bit different. You can't simply talk about the derivative at some x and y value, because how would you even define that? You can't fit a unique tangent line anywhere on this curve, so how are you going to talk about the derivative, for example, at that point? Now, in cases like this, you would have to resort to what is called partial derivatives, where, for example, you would fix x and then differentiate with respect to y, or you would fix y at some value and differentiate with respect to x. The derivatives you obtain in this way are called partial derivatives. The differential equations that you get when there are partial derivatives involved are known as partial differential equations. So that's simply cases where the unknown function has more than one independent variable, in which case the derivatives necessarily have to be partial derivatives. So for example, something like this complicated looking thing. This is a partial derivative in terms of a function psi, which, unlike the case on the previous page where psi only had two independent variables, this one has at least 4, x, y, z, and t. And this would be, or this is, the second order partial derivative of psi with respect to x. And for someone to calculate something like this, they would take psi, the expression for psi if they have it, and treat y, z, and t as a constant, and then simply differentiate twice with respect to x in the same way as you would differentiate any function with respect to x. And that it is a partial derivative is indicated with this funny looking d, which is like a reverse 6 or a flipped 9, which is specifically used to indicate that it is a partial derivative. We don't use it for normal derivatives, and likewise we don't use normal d's for partial derivatives. Now, we won't look at partial derivatives, partial differential equations for the right until the end of the course, when we will end with a lower dimensional version of this differential equation that you're looking at right now. This is the wave equation in 3 dimensions. We will end the course with the study of a lower dimensional version of it. And when we get to it, we will come back to partial derivatives and talk about them again. But because we are going over the basic and important notations and different terminology involved in differential equations, we include the definition at this point because it would be a glaring omission otherwise. Okay. Now, next definition is very simple, and that is just the order of the differential equation, and that is simply the highest derivative appearing in it. So here, for example, there are 4 derivatives. Each is a second order one, so the highest order derivative appearing here is 2, so the order of this differential equation is 2. The next definition I want to get to is particularly important. But before I do, I want to quickly go over what is meant by a linear combination of, say, 3 things. It could be more, it could be 4, 5, or whatever finite number, but let's just stick to 3 to keep it simple. The linear combination of x, y, and z is simply a constant times x plus a constant times y plus a constant times z. So something like this, or like this, or in general anything of the form ax plus by plus cz, where a, b, and c are constants. Real numbers for us, or complex numbers if you're working in a complex plane. Now x, y, and z, they could be anything that you could add or subtract, any elements of a vector space. So x, y, and z could be numbers, they could even be functions, or they could be matrices. Okay, so let's see if we can understand what is meant by a linear differential equation. Now this is nothing other than a differential equation that has this complicated looking form. It looks complicated, but only at first. It really isn't, if you look carefully at what's going on here. What you have on the left-hand side is essentially nothing other than a linear combination of y and its derivatives. Up to a point, up till if the nth one is the highest one, then it's called an nth order linear differential equation. So all you have is a linear combination of derivatives of the unknown function, with the one difference being that these coefficients are allowed to be function in terms of the independent variable x. So for any x value, they would be constants in the way that we defined linear combinations on the previous page. Now the important thing to notice here is that all these derivatives of quote-unquote freestanding, y and its derivatives are all freestanding. The only thing that is in front of them is functions or things in terms of x. That's it. You don't have something like cosine of this, or the square root of that, or 1 over this derivative, or y squared. No, y and its derivatives should all be quote-unquote freestanding. Nothing funny going on with them. They're not being multiplied with each other. They're all standing separately. They're not inside other functions. The only things in front of them are functions in terms of x, which includes just normal constants. And then what's left over on the other side should just be a function in terms of x only. And as a follow-up definition, if what is left over, this fx term, is 0, so if there's nothing left over, then the differential equation is called homogeneous. Otherwise, it is non-homogeneous. Now, it's important to understand that this is not simply yet another abstract definition. The approach to dealing with differential equations, in as much as finding solutions, is first and foremost to identify what kind of differential equation it is. And linear differential equations in this respect are very important. Why? Well, because they're both common, and the linearity of them is very, I suppose you could say, conducive to finding solutions. So there are some very nice tools that you have at your disposal to solve them if you know it is a linear differential equation. And luckily, a lot of relevant ones are linear. And a non-linear differential equation is therefore simply a differential equation that cannot be written in linear form. So it's just a differential equation that is not linear. It's not much of a descriptive term at all. All that it is telling you is that you do not have that very nice and pleasant to use linear property. So all of the nice tools that are available for use for linear differential equations cease to be valid in general. Right? It essentially represents the Wild West. It could be anything. So let us look at a couple of examples. This first one, what is its order? Well, there's only one derivative appearing and it's first order, so the order is 1. Is it linear or non-linear? Look at the structure again. This is a very nice example of a linear differential equation. There's only one derivative and it's nice and quote-unquote freestanding. So this is nice, simple linear form. For second one, what is the order? Well, again, there's only one derivative appearing and it is fourth order. So the order is 4. Is it linear or nonlinear? In this case, it is nonlinear because we've got two things that is a problem for linearity. First is here, I can't have the derivative inside cosine of x, so that's a problem. The derivative and y itself needs to be nice and quote-unquote freestanding. If it was cosine of x multiplied by this derivative, that would have been okay. But as it is, this is a problem. This makes it nonlinear. But even if this wasn't a problem, we still have a problem here because it's e to the y. That's also not allowed. Y can be by itself. You can have e to the x multiplied by y, but definitely not e to the y. This makes it nonlinear as well. So if it was cosine of x multiplied by this term, and here we had e to the x multiplied by y, then this differential equation would have been linear. But as it stands, it's nonlinear. As for this one, order, well, there are 3 derivatives. This one's order 2, order 1, order 3. So the order is 3. Linear or nonlinear? Again, nonlinear. Here I've already got a problem. The derivative to the power 3, so you're not allowed to have that. Remember that derivatives have to be quote-unquote freestanding. And I also can't have derivatives, 2 different derivatives, or any 2 derivatives multiplied by each other. So this is also a problem. So this is also a nonlinear form. As for the fourth one, 3 is the highest order derivative appearing, so the order is 3. And go and look at the structure again. This is a nice and linear structure. All the derivatives and y itself is nice and quote-unquote freestanding. So this is a very nice, pleasant-looking linear form. Now, because differential equations and derivatives are so ubiquitous in many fields, there are multiple notations for the same thing. So we want to cover some of the ones that we expect to see. But we start off by noting, though, that even though I suppose you could say it's good etiquette to name functions, like here we're saying there's some function y in terms of x and the name of that function is f, that is often simply omitted. So you could just say a function y equal to y of x, or just a function yx. So it's not unusual to simply not refer to the name of the function at all. Okay, now as for the derivatives, you're probably already familiar with the prime notation. Like you would talk about f prime of x, or you could just talk about y prime, or double prime for second derivative, or 3 prime signs for third derivative. But from fourth onwards, you use brackets like this, or for anything beyond 4. And you have to put the brackets, because if you don't put the brackets, then it means y to the power 4. So here are a couple of ways to write the same thing. Y prime of x is equal to y dx is the same as df dx if, or f prime of x if it has been specified that the function name is f. And y triple prime is third derivative, and y brackets 5 would be the 5th order derivative. And please don't get blinded by the fact that we often use y and x for this. Y and x and t don't necessarily always have to be the dependent and independent variables. You could have p's and q's and z's and whatever. So don't get too used to y's and x's all the time. And this is something you probably saw in first year already. If the time independent variable is time t, then the dots are used like this to indicate derivatives. You don't have to, but you can. We will typically, well, the y dot is dy dt, and x double dot, second order derivative x dt. I want to go higher than second order. I don't know if you necessarily would want to, but then I don't think you use 3 dots. Then you just revert to the prime or this bracket notation or this notation. So let us talk a little bit about why it is worth studying differential equations in the first place. We will study them in the context of vibrations and waves, or I suppose technically the other way around. But still, why is it worth looking at differential equations in any depth at all? The major reason is what is stated there. It is that the fundamental laws are in the form of differential equations. From Newton's second law to Schrödinger's equation in quantum mechanics to the Maxwell equations in electromagnetism. Those are all differential equations or can be written in the form of differential equations. In fact, the big thing about Maxwell, the big breakthrough of Maxwell's equations was exactly that he set out to write the known electromagnetic phenomena in terms of differential equations, which directly led to the prediction of things like electromagnetic waves and all the rest of it. So whenever you do analysis of processes and systems in using those fundamental laws, in one way or another, you end up with differential equations or something that can be written in the form of differential equations. But even if you aren't, even if you're looking at something like Newton's second law of cooling, where you're trying to model the temperature of some object in the environment, and then you use Newton's law of cooling, which is motivated by experiment, by saying that by starting off by assuming that the rate at which the object's temperature changes is proportional to the rate of change of the difference between the object's temperature and the environment's temperature, then of course you'll end up with a differential equation that you have to solve. And there, note, your starting point was assuming something based on experiment about how fast that which you were after is changing, in this case the temperature. And it's that kind of scenario in which you know a little bit something about how fast the thing that you're after is changing that puts you in the realm of differential equations, something that is perhaps at first surprisingly common. And if you can do that, then you open yourself up to the differential equation theory, where you can use a bunch of tools and techniques to advance the analysis and come to conclusions, which is what we will see for vibrations and waves. But before we get to that, let's look at a couple of examples to see how differential equations come about in a very natural and direct manner. Okay, so exercise 1. Write down the differential equation for the velocity of a body falling in a vacuum. Okay, so presumably on Earth. So I've got my object falling with a certain velocity. Well, let's just, for purposes of this exercise, treat velocity as a scalar function. Right, for me to write down a differential equation for it, I need to write an equation in terms of its derivative or one of its derivatives. So do I know something about its first order derivative, its first derivative? What is the derivative of velocity? It's acceleration. And what's the acceleration going to be? Quite correct, 9.8. And I don't use units because it's a differential equation. It's cumbersome to keep track of units in differential equations, so we don't, pretty much as a rule, don't use units in differential equations. We reserve the use of units more for final answers, like where is something? Well, at x equal to minus 3.5 meters, then we'll use units. But in the context of differential equations for the constants and coefficients, I won't use units. Okay, but like I said, this is a little bit of abuse of the notation because velocity is really considered a vector valued function. So just to avoid any confusion there, formally, the velocity is a vector with 3 components. Let's view if you use axis x, y, and z with a x component and a y component and a z component. And let's say x and y is parallel to the surface of the Earth, and z is straight upwards, and it's just falling straight downwards, not with any initial x or y, any initial velocities in the x or y directions. So then it's just falling straight downwards, and then we'd say that the derivative of the z component is 9.8 or minus 9.8, depends on how you set up the axis. Okay, so we'll just be formally more correct because we consider velocity a vector. Okay, but for the purposes of just showing where differential equation comes from, this is okay. Now, second one. Write down the differential equation of the displacement of a body falling in a vacuum. Okay, so now I want to talk about a displacement function, and to indicate that on the diagram I need a set of axes. Well, we tend to think of y as vertical when we're in 2 dimensions. Let's use y. So in this little object falling, and let's say I've got my vertical axis y upwards. Let's say upwards is positive, That's what the arrow is for, indicating that upwards is positive. So please don't ever put arrows on both sides, only on the side which indicates the positive direction. And its displacement is given by some function y of t. And I want to write down a differential equation for y of t. For aesthetic reasons, if it will help, you can put it on the ground if you really want. Okay, and 0 could be there, could be there, could be anywhere. Right, so I want a differential equation for displacement. That means I want an equation in terms of the derivative of y. Okay, so, or one of its derivatives. Well, I know that the derivative dy dt, this is going to be the y component of the velocity. And do I know something about this? Well, I do know from the first equation that the derivative of this second derivative, dy dt squared, is dvy dt. And this is, what is the derivative of the y component of the velocity? It is the y component of the acceleration. And we know what that is. So I don't know directly something about dy dt, but I know something about the second derivative of the displacement, because that is the acceleration, and that is what? Minus 9.8 in this case, not positive 9.8. Why? Well, because of the way I set up the axis. Now up is positive. As it's falling, y is decreasing, so the velocity, the y component of the velocity, the derivative of y is negative, and it's becoming more negative as it's falling, so because the accelerating, so the velocity is also decreasing, so the derivative of the velocity, the acceleration, is negative. Or you could just reason, well, it's accelerating downwards in the negative y direction, so acceleration is negative. Anyway, so there we go. Okay, so for exercise 3, we're looking at two negatively charged metal spheres with given charges and masses and initial distances apart, and both spheres are initially at rest. And we're supposed to get the differential equation by using Coulomb's law and Newton's second law. Now, strictly speaking, we did use Newton's second law already for the earlier problems. Now, it's very important for you to understand how where the differential equation comes from by using Newton's second law. And now, what does the law state? First of all, it said mass times acceleration is equal to the force on the object. Now, this is really three equations because these are vectors. So it's really the mass times x component of the acceleration, y component, z component is equal to fx, fy, fz. So the three equations is the mass times the x component of the acceleration is equal to the x component of the force, and the mass times the y component of the acceleration is the y component of the force, and the mass times the z component is the z component of the force. And this is where the differential equations will come from. Okay, but often we will recognize that it's sufficient to just work in one axis, not two or three, and then we'll just use one of these at a time. And for example, in this problem. Good. But really it all comes from here. Good. So let's start. So I've got two spheres, 1 and 2, and they're only going to be moving in a line connecting the two of them, so it's only necessary to specify one axis. So let's make it x. Let's say to the right is positive, and there is the displacement of the first one is given by x1 of t, and displacement of the second one is given by x2 of t. And you can put down 0 if you want. You don't have to, doesn't matter for purposes of differential equation. All right. Okay, so what do we know? From Coulomb's law, we know that there's going to be a force on the one due to the second in the direction directly opposite to the line connecting the two of them. There's a force on the first one due to the second, and the same magnitude force in opposite direction on the second. Good, like that. Right. And I know what the magnitude of these two forces are. F1, F21 is equal to K times, alright, this is high school stuff, Q2, Q2 over distance between them squared. though the distance at any t between them will be the difference between the two displacement functions. This distance is the difference between these two, x2 minus x1. So this I can just write as k, q1, q2 over x2 minus x1 squared. Good, and now I just use Newton's second law, and I'm just in one axis, so I can just work with that. Right, so for the first mass, so this is Newton 2. Right, so the mass of the first sphere times its acceleration in the x direction. So let's directly write that in terms of the derivative. So that would be the second derivative of the acceleration of the displacement. dt squared is equal to the x component of f12. And I know what that is. What's that going to be? Well, it's going to be minus this because it's in the negative x direction. So minus k q1 q2 over x2 minus x1 squared. Good. Okay, and similarly for the second one, it's going to be second mass of the second one times its acceleration in the x direction, dt squared is equal to f21x is equal to, but it's going to be positive, k q1 q2 over x2 minus x1 squared. And there we have it. Here are all the differential equations, the system in this case. The first derivative of x1 is in terms of x2 and x1, and likewise for x2. All right, so this is a bit more tricky to solve, but it is solvable. The point is not here to solve it, just to show how easily you can write down the differential equation or system of differential equations, such as in this case. Now directly it follows from Newton's second law. Solving it is a different matter, but it should be obvious to you that you can do the same thing for 3 or even 4 spheres. It could be slightly more complicated, but not more difficult, not really. But as soon as you move to 3 spheres, then you've got the infamous 3-body problem, and even though it's simple to write on the differential equations, it's no longer solvable. There is a solution, just can't get it. Okay, so on to 4. Okay, so for exercise 1, 2, and 3, we relied on fundamental laws to arrive at the differential equation. But as we'll see from the remaining problems, you don't have to be doing analysis in terms of fundamental laws to arrive at differential equations, even though in the background those laws obviously still continue to play a role. So let's look at exercise 4, in which we have to write the differential equation that's a mathematical model for each of those situations described. What is A? That is just Newton's law of cooling. Rate of change of the temperature of the body is proportional to the difference between its temperature and the environment's temperature. So nothing simpler. The time rate of change of the temperature is some constant times the difference between the temperature of the object, cup of coffee, or whatever it is, and the environment. And see if you can understand why, in this case, the constant would have to be negative, some negative real constant. And to find it, you would actually have to take some measurements of the cup of coffee at 2 different points in time. Okay, so that's all there is to it. B, all right, so Torricelli's law, that the time rate of change of the volume of water in a draining tank is proportional to the square root of depth of water in tank. Well, it's not stated, but it's pretty clear that has to be the case. That its depth from the outlet. All right, so let's say it is a bit of water in some tank, doesn't matter what shape it is, and the water is flowing out, and its depth at a given point is given by y of t. All right, so then dv dt is some constant times square root of y. All right, there's a differential equation. And in this case, k would have to be also negative. See if you can understand why that must be the case. Right, C, which is unfortunately more relevant than I would like. It says that in a city with a fixed population of people, the time rate of change of the number of people affected with a certain contagious disease is proportional to the product of the number of people who have the disease and the number of people who don't. Okay, so let's say that P is the city population and Q is the number of infected. Then, if that is to be believed, then it says that the rate of change of the number infected is proportional, so some constant, times the product of the number that's infected with the number that isn't. So that would be P minus Q. Okay, and there it is. Simple differential equation that could at most be relevant for some window of time. Okay. Right, so exercise 5. We have to consider an RC circuit, which is a very common kind of circuit, in which an EMF Xi is applied to resistance R and capacitor with capacitance C in series. Then, using Kirchhoff loop rule, derive a differential equation for the charge Q on the capacitor. Okay, so let's quickly redraw. Now, of course, if you can't quite remember Kirchhoff loop rule, then perhaps just pause and quickly go and revise that. So here's my EMF source, my resistor R, and my capacitor C. And okay, right. Okay, so I'm not sure, I think you worked with capacitors in first year, but in any case, what you need to know about capacitors for this problem is not much. It's just that it's basically two parallel plates like this, and as soon as you connect it to a voltage source, then the one side becomes positive and the other side becomes negative, and it keeps charging until the voltage across it is the same as the source voltage. And capacitors you've probably seen, well, definitely seen in circuit boards or anything electronic really, almost anything electronic. They're usually these little cylinders, two little connectors, and they're just little cylinders like that, because to do this arrangement of two parallel plates, the capacitor is stronger the larger this parallel surface area and the closer the two plates are to one another, and depending on the material you put between them. So to do this optimally, they use two kind of rolled plates that are rolled up inside of each other anyway, like that. So to do that efficiently, they use this kind of technique, and that's why it's these little little cylinders in circuits, and they can explode quite spectacularly if you try to overcharge them. Anyway, so the charge at any point in time, the charge on the capacitor is related to the voltage across it with a simple formula, Q equal to CV. So charge coulombs, farads, and volts. And if Q is, let's say, 10 microcoulombs, then that means the positive plate has a charge of plus 10 coulombs, and the negative plate has a charge of negative 10 coulombs. And of course, this does not happen immediately. We're after a differential equation, so that means necessarily something is changing. And what is changing in this case? It is the charge on the capacitor. As soon as you close this circuit, it's not immediately going to reach its maximum charge. It's going to be a gradual process. The electrons are going to stream to the one side and away from the other side. So by setting with the differential equation, we'll be able to look a little bit more closely to how that happens. Now, I don't expect it to be clear where exactly the differential equation is going to come from, so you should view the use of the Kirchhoff loop rule as a hint in this case. So let's just use it. So let's go clockwise. All right, where's the current? Conventional current, of course, is also clockwise. All right, so let's start here. Negative to positive, so that is Xi, and then conventional current going in the same direction as the conventional current over the resistor. So this voltage, it's going to be minus that voltage change, which is going to be IR. And then I get here, and what do I have from positive to negative, higher to lower potential? It is going to be also negative, whatever this voltage difference is, and that is V, which is what is V? It is just 1 over CQ, so minus 1 over CQ, and that is equal to 0. Right. Okay, so where's the differential equation then? Now, if you go back in your first year textbooks and see how current is defined, you should most likely you'll find something like this, that it is defined as dq dt, where dq is the amount of charge that moves past a point in a small span of time dt. Now, so yes, it is in this case, so, I messed up the xi, okay, minus I, in this case, the current in the circuit is just dq dt, minus 1 over CQ equal to 0. And that is in the differential equation, where Q is the unknown function of time. Now, if this bothers you a little bit, then that's a good thing. But what should bother you a little bit is the way that Q is used in the definition of a current in your textbook is not exactly the same as the way Q is used here. In this definition of the current, the Q would refer to the amount of charge moving past the point we're trying to define a current, where here Q very specifically is the charge on the capacitor plates. But it is still going to be the case, if you think about it, that the time rate of change of the charge on the capacitor plates, that is still going to be the actual current in the circuit. Well, you can think of that in two ways at least. First is just what would it mean, for example, if this dq dt, the time rate of change of the charge on the plates, if that is, let's say, 1 coulomb per second, then that means at that point in time, the charge on the plates or the charge of the capacitor is changing at a rate of 1 coulomb per second. In other words, that the positive plate is increasing at a rate, its charge is increasing at a rate of 1 coulomb per second, and the negative plate is, its charge is changing at a rate of negative 1 coulomb per second. So it should make sense if you think about it, that means that it is being fed with a current of 1 coulomb per second on one side and negative 1 coulomb per second on the other side. Another way of thinking about it is to use the water analogy, where electrons flowing in a current is viewed as water in a pipe. The water analogy and pressure analogy is often used to get an intuitive hold on what is going on in circuits. So in that case, a capacitor, which is just a device for storing charge, would correspond essentially to a tank. So let's say you have a tank that has been filled up with water with some sort of hose or pipe, and this tank is slowly filling up, and let's say you see that the rate at which the volume is changing is 1 liter per second. Then, of course, I think you'll agree that means that the flow in the pipe that's feeding the tank is also 1 liter per second, which is the same reasoning used to reason that the time rate of change of the charge on the capacitor is equal to the current I. Though this is slightly imperfect analogy in that it's two plates, so really we should be talking about two tanks, but that won't change the fact that the current I is given by dq dt. Okay, now some of you are taking W2W286, at least I hope some of you are. So for those of you that are, you should, I think, be able to go through or work through a solution for this and find a solution for this differential equation. If you assume that the capacitor is initially neutral, has initially no charge, at T0 has no charge, so in other words that Q0 is 0. If you do that, then you should be able to find that, derive that this is, and perhaps you know, it's a pretty standard thing there, so it's probably done as just a simple example in your differential equation textbook anyway. This should give you C xi 1 minus e to the minus t over RC. Now, I don't expect you to be able to derive this as part of the coursework. This is outside of the scope of vibration waves, but you should at least be able to, and this will be an exercise included at the end, you should at least be able to see that this is a solution of this differential equation. In other words, if I plug this Q into the left-hand side, then yes, I do get 0. Okay, and for interest sake, if this is the charge, we perhaps not as interested in the charge itself, perhaps more the voltage. So the voltage is 1 is the charge divided by C. So if I divide by C on both sides, I'm going to get the voltage at time t, and that will be xi 1 minus e to the minus t over rc. And it's high school work to determine what this thing looks like, and it looks like what it looks like makes sense. It looks like this, if you think about it. Asymptote there, xi, max voltage, it's going to look like this. So initially at time 0, the capacitor plate's neutral, and then it quickly starts to approach the maximum voltage, which is the source voltage. And then you can, with basic calculations, determine, how long is it going to take for the capacitor to charge to, let's say, 80% of its maximum capacity. With typical resistance and capacitance values, you should get very short time spans. Okay, so an additional exercise for those up for it would be to try to find a similar differential equation for the case where you discharge a capacitor, because that's how discharge capacitors, just to connect the two endpoints to a resistor, and then you should be able to try and set up a differential equation again. And if you're up for it, or if you're capable, then you can also try to find a solution for it and see what that looks like and how long that takes for the capacitor to discharge. Okay, all right, but that's it for this problem. Right, so next one, exercise 6. We have to consider a DC generator in which an EMF xi is applied to resistance R and an inductor with inductance L in series. And then, similar to previous problem, using Kirchhoff loop rule, derive a differential equation, but now for the current in the circuit. Okay, so let's quickly redraw it. So my EMF, my resistor, and my inductor, which in the simplest case is just a solenoid like this, and it's got some inductance L, which will be determined by the dimensions of the solenoid and the amount of turns it has and so on, and the conventional current in this case. Okay, now again, I'm not sure if you worked with inductors in first year, but even if you didn't, there's not much you need to know to do this problem. It is just essentially a solenoid like this in the simplest case. And if there's current flowing through it, then, as you probably know, then it turns the whole thing into essentially a bar magnet with magnetic field lines going right through the center of the solenoid. The important thing is, if the current is constant, then there's nothing special going on apart from the thing just acting like a big magnet, made stronger by putting in an iron core, turning it into an electromagnet. But if the current changes, because the current is not immediately going to be a certain number of amperes. It's initially, if you close the circuit, it's going to increase. If the current changes through an inductor, through a solenoid like this, then very roughly speaking, the amount of magnetic field going through the coils changes. And then, by Faraday's induction law, there is an induced EMF, which we can indicate like this, xi L, self-induced EMF that tries to oppose that change. If it's increasing current, then the induced EMF will act to decrease it. If it's a decreasing current, then the induced EMF will act to increase it. Most likely, Faraday's law for magnetic induction was at least mentioned first year, if you did not look at it in any detail. But in any case, it's something worth knowing, because that's the working principle behind electric motors and electric generators. Okay. Now, the induced EMF in the direction of current is always just going to be minus L times di dt. See, it depends. It's nothing special going on if the current is just a constant. But if the current is changing, then the amount of magnetic field or the magnetic flux through the coils change, and then you've got an induced EMF. and it is always in the opposite direction to the change, which is where the minus comes from. That is called Lenz's law, which you can use to determine in an electric generator in which direction the current is going to be generated. Okay, but anyway, so all you need to know for this problem is that if the current is increasing or decreasing, in this case increasing as the switch is closed, the current through the inductor changes, it's increasing, and the induced EMF in the direction of the current is just minus L di dt. It's an EMF that's induced due to the magnetic flux changing, due to the strength of the current in the coils changing. Okay, good. So now it's the same thing. Let's just use Kirchhoff loop rule, and we get Xi, and there the same story as before. And then here comes plus Xi L equal to 0, but that we know. This is minus L di dt equal to 0. And that's it. Nothing fancy going on beyond that. We kind of directly get to the differential equation. And you'll notice if you look back at to the previous problem, that the form of the differential equation is essentially the same. It is the same. So you should be able to similarly, from the solution that I gave for the differential equation in that case, you should also be able to find a solution for this one. Then look at what it looks like and see if that makes sense to you. Okay. But we will return to this inductor and capacitor story in the next lecture. I mean, something very interesting happens if you connect the two to each other with connection to vibrations and waves. Okay,